So welcome everybody to our usual, by now, right, it's the first time we're already running the seminar, Combinatorics seminar. It's a great pleasure to have today Wojciech Samotij. Again, you can read Wojciech's biography online, right? Wojciech did really many great things already in combinatorics. And today he will talk about Simonovits theorem in random graph. Please, Wojciech.
Thank you, Benny. Thanks very much for the invitation, and thank you all for coming. The topic of my talk is indeed Simonovits theorem in random graphs, and this is joint work with one of my great graduate students, Ilay Hoshen, whom you can see there in the chat. So let me start the talk. So let me start with the basics. You probably all know Turan's theorem, which for every R determines the largest number of edges in a subgraph of Kn, so a graph on the vertices, which doesn't have Kr plus 1 as a subgraph. Now, maybe not all of you know, but Turan's theorem actually says something slightly stronger. It says that the largest R-partite subgraphs of Kn are in fact the unique maximizers of this parameter. So every largest Kr plus 1 subgraph of Kn is indeed R-partite. It's the balanced R-partite subgraph of Kn where all the color classes differ in size by at most 1. A slightly less known generalization of this theorem due to Simonovits from 1974 states that the same is true for a graph with chromatic number R plus 1 and n sufficiently large if and only if H is so-called H critical. So what does it mean that a graph H is H critical? There are two equivalent definitions. One is that there is an edge of H whose deletion reduces the chromatic number. So you may note that the clique is such a graph, because if you delete an edge, then the chromatic number goes down from R plus 1 to R. And an equivalent definition is that you may find a copy of a graph is H critical if you may find a copy of H in the complete chi H minus 1 partite graph. It's enough to add one edge to it, and this already gives you a copy of H. For example, if you take the complete bipartite graph and you add an edge, then you will find there not only a triangle, but also every odd cycle. And this shows that odd cycles are examples of H-critical graphs. So two examples of families of H-critical graphs to keep in mind are cliques and odd cycles. Now, we can, not to say all the time that all the largest R-partite H-free subgraphs of G are the largest chi H minus 1 partite subgraphs. I will introduce this notion of a graph G being H Simonovits, which says that precisely that the largest H-free subgraphs of G are its largest chi H minus 1 partite subgraphs. So Turan's theorem, we could say, states now that Kn is Kr plus 1 Simonovits, and Simonovits' theorem, even though it wasn't stated this way, it says that Kn is H Simonovits if and only if H is H critical. Now, the topic of the talk will be, we will study for which values of P is the random graph G and P asymptotically almost surely Simonovits for a given H critical graph H. So note here that we'll be interested in P tending to 0 with n, even though the early results in the area concern constant P, and we'll be interested in getting the optimal sufficient conditions that guarantee that a typical sample from G and P is H Simonovits for a given H critical graph H. Now, the first authors to consider this question were Babai, Simonovits, and Spencer in 1990, who proved that P being at least at most 1/2, so P is at least 1/2 minus some small positive constant, then G and P will be typically Simonovits with respect to an odd cycle. So a triangle, a C5 or a C7. They also asked whether this assumption that P is at least 1/2 could be reduced to something tending to 0. And this took quite a lot of time. The next work on this topic is a nice paper of Brightwell, Panagiotou, and Steger, who proved that for every clique, GNP becomes KR plus 1 Simonovits if P is at least N2 minus some small constant that depends on the order of the clique. So in particular, if we're interested in generalizing Mantel's theorem, so when are all largest triangle-free graphs of GNP bipartite, according to the theorem of Breithold, Panagiotou, Steger, you need to assume that P is at least N to the power minus 1 over 250. So some very small polynomial in N. Now, what would the optimal condition guaranteeing this be? So let's first talk about possible lower bounds. So under what, if GNP will be sufficiently sparse, then this will be not true. And to convince you that this is the case, let's note the following observation. Suppose that H contains some subgraph, let's call it F, so that the expected number of copies of this subgraph, which is of the order of n to the number of vertices of F times p to the number of edges of F, is asymptotically smaller than the expected number of edges n squared p. And moreover, I will assume that n squared p tends to infinity, otherwise the graph expects to have constant number of edges. The problem is not interesting. In this case, since the expected number of copies of any graph F is much smaller than the expected number of edges, this also happens typically. And one can produce an H-free subgraph of GNP by taking an arbitrary edge from every copy of F and removing it from the graph. Since the number of copies of F is much smaller than the number of edges, we barely touch the graph. We still have almost all the edges left. However, since we removed all the copies of F, we also removed all the copies of H, and we obtained an H-free subgraph, which contains essentially all the edges of GNP. And this assumption shows that the number of edges of GNP actually concentrates around this value, so we have this asymptotic equality. However, if we further assume that the number of edges is at least linear, then the number of edges in R-partite subgraphs of GNP concentrates around its expectation, which implies that any R-partite subgraph of GNP would contain at most 1 minus 1 over R proportion of the edges. So in particular, the largest H-free graph is significantly larger than its largest R-partite subgraph, and therefore GNP is typically not H Simonovits, even if H is H critical. So this leads to the following necessary condition. For every subgraph F of H, we need the expected number of copies of F to be at least of the same order as the number of edges. Otherwise, the theorem is obviously not true. Now, let me restate this necessary condition here. So we said for every subgraph, which is non-empty of H, the number of copies of the subgraph is at least of the order of the number of edges. And this is typically rewritten in the following concise form. P is at least a small constant times n to minus 1 over m2 of H. And this m2 of H is a graph parameter called the two-density of H. It's the maximum ratio of the number of edges of F minus 1 divided by vertices of F minus 2, where F runs over all subgraphs of H with at least 2 edges. So you might have seen this parameter before. If not, this is precisely what comes out from that calculation. Now, we will say that H is too balanced if this maximum is achieved by H itself. And moreover, a graph H will be called strictly too balanced if the maximum is achieved only at H. So for every F which is not H, this ratio is slightly smaller. And in the remainder of the talk, I'll be mostly interested in graphs that are strictly too balanced. And just to say that it's kind of not a vacuous assumption, then both cliques and odd cycles are strictly too balanced, and there are many graphs that are strictly too balanced, but the two interesting examples of edge critical graphs have this nice property of being strictly too balanced. Okay, so we have this necessary condition, and it's now natural to ask, what can we say about a largest H-free subgraph of GNP once this necessary condition is satisfied? And kind of this was a very big open problem in probabilistic combinatorics for many, many years, until eventually it was solved by Kahn and Gowers about 11, 12 years ago. What they proved is that if the edge density P is asymptotically greater than this n2 minus 1 over the 2 density, then asymptotically, almost surely, every largest H-free subgraph of GNP is perhaps not exactly chi H minus 1 partite, but it's approximately chi H minus 1 partite, provided that H is strictly two balanced. And what do I mean by approximately chi H minus 1 partite? I mean that if you take the largest subgraph, H-free subgraph of GNP, you can remove a small proportion of its edges to make it chi H minus 1 partite. Also, an important remark is we don't need to assume here that the graph is edge critical. This holds without the assumption, because we don't aim to say that it's exactly chi H minus 1 partite, but only approximately. Now, this technical assumption that H is strictly two balanced was present in the original work of Kahn and Gowers, but it was later removed by a modification of an alternative proof of related results due to Schacht. And now this theorem is true with no assumptions on H. Okay, so this shows that under this necessary condition, at least we have the approximate version of the theorem we seek. And kind of for the rest of the talk, I will speak only about exact results. So we're asking under what assumptions on P, if we further assume that H is edge critical, can we remove the word approximately from the statement of the theorem? So to get a bit kind of more mileage from our lower bound assumption, let's consider the following notion here of a subgraph of G. So suppose we have a large graph G in our think edge critical graph H, and defined by G superscript H, this will be the subgraph of G, which comprises all edges that do not belong to a copy of H. Now, an easy observation is that if we consider any maximal H-free subgraph of G, then it must contain all these edges. Why? Because I can always add them without creating a copy of H. They don't even create a copy of H with all the edges of G. So in particular, they don't close a copy of H with this largest H-free subgraph. Now, if the largest H-free subgraph of G has chromatic number less than chi of H, then this also must be true about the graph GH, because it's contained in every maximal and therefore every largest H-free subgraph of G and P. So one necessary condition would be that typically, if we calculate this subgraph in G and P, its chromatic number must be smaller than the chromatic number of the graph H. And let's maybe do a quick example here when H is the triangle. So what is the probability that a pair of vertices belongs to this triangle subgraph of G and P? As we said, the edge itself must be an edge of G and P. So for this, we get probability P. But also, it must not belong to any copy of the triangle in G and P. So this edge lives in n-2 triangles, and none of them can appear in G and P. And this is exactly the probability of 1 minus p squared to the power of n-2, because these events are independent. So all in all, we get roughly p times e to the power np squared. Now, let's take p to be a constant c times 1 over square root of n times a factor of square root of log n. This value is the n2 minus 1 over the 2 density of the triangle. So compared to our previous necessary condition, we added this square root of log n factor. Under this assumption, the probability that a given pair of vertices is an edge of our graph G and PK3 is roughly n2 minus a half minus c squared up to logarithmic factors. Suppose now, for the sake of the argument, that this graph behaved like the random graph with independent edges with the same density. Then this density Q would be n2 minus a half minus c squared. Now, if the exponent here is bigger than -1, then G and Q, where Q is much larger than 1 over n, already has chromatic number, which is unbounded, because its independence number is sublinear. In particular, we can suspect that if the c squared plus a half will be less than 1, then our graph G and PK3 will have unbounded chromatic number, which means that G and P cannot be H Simonovich, because even the edges that are in no triangles already, they generate a subgraph with unbounded chromatic number. And a rigorous version of the argument is that if P is at most this constant times 1 over root n times square root of log n, then maybe we cannot show that the chromatic number is unbounded, but it's enough to show that the chromatic number is larger than 2. So we can, for example, show that it contains the 5 cycle. And this can be done with not so much work. So under this assumption, a typical sample from GNP contains 5 edges which form a 5 cycle, and moreover, none of these edges belongs to any triangle. And in particular, every largest triangle-free subgraph of GNP at this density contains the 5 cycle, which means it's not bipartite. Now, this shows that in order for GNP to be K3 Simonovich, we must be above this threshold. Now, this kind of argument generalizes to every strictly two-balanced H, which is H critical. Namely, we can have some positive constant CH, such that if P is at most, this is the 2 density, and we added here a logarithmic factor, log n to the power 1 over the number of edges minus 1, then under this assumption, the graph of edges which are not contained in a copy of H has chromatic number, which is at least the chromatic number of H, and therefore the graph GNP itself is not H Simonovich. Now, this then becomes a necessary condition that we need to assume in order to show that typically the graph will be H Simonovich. And maybe this would be a natural guess of the threshold for the property that G and P is H Simonovich. This was shown to be the case first in the case where H is a triangle by DeMarco and Kahn in 2014, who proved that if we replace this little CH, which was 1 over square root of 2, by some large constant C, then in fact, G and P will become typically K3 Simonovich, and maybe without this terminology, explicitly what it says that at this density, every largest triangle-free subgraph of G and P is bipartite, and we have an exact generalization of Mantel's theorem to the random graph. One or a couple of years later, they generalized their theorem to the case of larger cliques and proved that if P is at least the respective threshold, then the random graph is typically KR plus 1 Simonovich. So we have now an exact analog of Turan's theorem for the random graph GNP under optimal assumption on the density up to the value of this constant. DeMarco and Kahn in their paper from 2015 have had several conjectures, and one of them, which Ilay and I got interested in, was the following. It asked to generalize their theorem from cliques to arbitrary edge critical graphs. And what did they suspect for the threshold? They suspect that if every edge of GNP is contained in a copy of H, which in our language says that our graph GNPH is empty, then GNP should be typically H Simonovits. Now, one reason why we assume in our work that H will be strictly to balance is that one can fairly easily explicitly calculate this, and this threshold for the property, and this is the 2 density times a logarithmic factor, exactly like in the proposition above. So it's easy to calculate this, to give this lower bound, but also their guess for the threshold agrees with this calculation. And what I want to speak about in the rest of the talk is a solution to this conjecture under the extra technical assumption that our edge critical graph is strictly to balanced, which I recall it means that the ratio of the number of edges -1 divided by the number of vertices -2 is uniquely achieved at the graph H when we calculate this maximum over all of the subgraphs. Now, our theorem, in fact, gives here an explicit constant so that if P exceeds this constant plus anything positive times the threshold, then the graph GNP typically has the property of being H Simonovits. And we believe that this constant is optimal. However, at the moment, we're unable to prove it. I'll say a few words about this in the end. But since we do believe that the constant is optimal, let me try to explain what this constant is. And instead of kind of defining it as a number, I'll explain where it comes from. So what is drawn here is we have one edge between 1 and 2, and I've divided the vertex set of GNP into R classes of equal size. So here, R is the chromatic number of H minus 1. Now, instead of drawing here the complete bipartite graphs between the classes, we keep edges with probability P. But this edge is added with probability 1. And now the question that we're asking is H contained in this graph? If P was equal to 1, then H is contained in the graph precisely because it's edge critical. So we can find a copy of H in the complete multipartite graph with R classes if we add just a single edge. But here we keep these edges with probability P, and we're asking about the probability that H is not contained in here. Now, the threshold is defined by the following equation. We want this probability multiplied by n squared p, which is the expected number of edges, to be negligible, to be n to the little o of 1. Now, how is it related to this theorem? Suppose that what I drawn here was the largest R-partite subgraph of GNP. If I can add this edge without creating a copy of H, then we created an H-free subgraph which is larger than the largest cut. And why this n squared p? Because I will have n squared p edges here typically in this class, so I can try to do this n squared p times. And we believe that this gives the threshold. However, we can only prove the respective one statement, meaning that if we're above this threshold, then all the largest H-free subgraphs will be chi H minus 1 partite, but we cannot prove that below the threshold we can find some largest cut where this heuristic can be made rigorous. So this we're unable to do. Now, let me give you kind of a few ideas.
Wojciech, is it also applies even for triangles? So this constant we don't know in any of the cases?
So this constant you can easily compute.
No. What I mean the
zero statement. No, even for triangles. I mean, we tried, but as you will see later, I'll get to it on my last slide. Kind of what the challenge there is.
Okay.
Because in kind of, or I can say now that the largest cut should have at least as many edges as a fixed cut. And the challenge in proving the lower bound, you have to say that the largest cut is not much better than a fixed cut.
I see. Okay.
So here's some proof outline. I'll try to highlight a few ideas from the proof. What is our goal? Our goal is to prove that every largest H3 subgraph is chi H minus 1 partite. I don't want to say chi H minus 1 partite all the time, so I'll just denote chi H minus 1 by R. G is the GNP, and F is some largest H3 subgraph of G. Now, also by BR, we'll denote the largest size of an R-partite subgraph of G. Suppose that the theorem is not true for our G, meaning that F is not R-partite. And let pi be a partition that minimizes the number of edges that do not cross it. So here I'll use this notation, given a partition here in two parts. F intersection pi will be the edges crossing the partition, and F minus pi will be edges that do not cross the partition. So here I just view pi as the complete multipartite subgraph with these parts. And then F intersection pi will be the edges in this multipartite subgraph. F minus pi will be the edges of the cliques that are its complement. Now, if the graph is not R-partite, then even the best partition has some edges that do not cross it. However, Conlon and Gowers already told us that the number of edges not crossing the partition cannot be too big because the graph is approximately R-partite, and therefore the best R partition will have only relatively few edges that are not crossing. Now, a key notion here in the argument is the notion of a deficit of a partition. So the deficit of a partition is how far is this partition from a largest one. So partitions with deficit 0 will be those partitions where the number of edges crossing them is maximal over all partitions. And if partition has small deficit, then it means it's close to a largest cut. And this is the key inequality. Since the chromatic number of our graph is larger than R, it means that the largest R-partite subgraph is an H3 subgraph, which means that the largest H3 subgraph is at least as large as the largest R-partite subgraph. Now, the number of edges in this graph is the number of edges crossing its optimal partition, plus the number of edges which doesn't cross its optimal partition. And this BR, we can write in terms of the same partition. By the definition of the deficit, it's the number of edges of G that cross the partition plus the deficit. Perhaps this is not the optimal partition for G, because we assumed it's the optimal partition for F. And to get a contradiction here, it would be enough to get a reverse inequality, meaning that the number of, among the edges crossing the partition, the number of edges that belong to G but not to F is strictly larger than the number of edges of F that do not cross the partition minus the deficit. So in particular, if F, say, had only one edge not crossing the partition, and the optimal partition of G would be the same as the optimal partition of F, then we need to show that we had to delete more than one edge from edges crossing the partition so that we couldn't add this edge F for free. Now, why would we even expect this to be positive? Namely, if we add some edge which doesn't cross the partition, then we have lots of possibilities to close a copy of H here. And therefore, for every copy of H, we will need to remove at least one of its edges. And this is how the whole argument is built. And I'll make this precise on the next few slides. So recall my notation. G is a sample from GNP. R is the chromatic number of H minus 1. F is some largest H3 subgraph of G. Pi is the largest R partition in F. And the deficit of pi is how far from optimality is this partition when viewed as a partition of G. And BR here is the max, the largest R-partite subgraph of G. So now the key notion here is the notion of Q-supported pi-crossing copies of H. Let's fix some subgraph of F, call it Q, and a copy of H will be called Q-supported pi crossing if other than the edges of Q, all the other edges are in G and cross the partition. So here are two illustrations. This is, if Q is the red graph, then this is a pi crossing Q supported copy of the 5 cycle, because all of its edges apart from the edge of Q cross the partition. And here we have two different Q supported pi crossing copies of the triangle. Here Q is one edge and we have this path of length 2. Here when Q is 2 edges, this triangle is also Q supported and pi crossing, and it has only one edge in G. And the key observation is that since we assume that Q is a subgraph of F, we know that F contains the red edges. But F is also H-free, so it must avoid at least one of the blue edges. But all the blue edges cross the partition, and therefore this will contribute to the lower bound on the number of edges of G, but not in F that cross the partition. Now, we need, of course, more than one such edge, and therefore the way to make this lower bound precise is to say by this FQ pi, we will define the sets of blue edges for every Q supported pi crossing copy of H. So here FQ pi will be this path of length 4, and here FQ pi will be this path of length 2 and this edge. Now, since for each such copy I need to remove at least one edge from G when I construct my F, it means that the total number of edges I remove will be at least the smallest size of a dominating set for this set of edges, but the smallest size of a dominating set will be lower bounded by the size of a matching. Meaning if we find a number of pairwise edge disjoint such copies, then from each of them we'll need to remove at least one edge, and this will give us a lower bound. Here, let me state an important remark is that when I say a matching, I don't care if they share the edges of Q. So if I said here on one edge of Q, I had many such 5 cycles, the only thing I care about is that these paths of length 4 will be pairwise disjoint, because we're guaranteed that this Q is in F, and we know that we will not remove it. We only remove the blue edges. So kind of now our focus will be how to lower bound this matching number of this family of subgraphs FQF. Sorry, FQ pi. So again, let me repeat the definitions here. FQ of pi is the set of blue edges of all the Q supported pi crossing copy of H, where Q and pi are my parameters. What we need to get a contradiction that will prove our theorem is to lower bound the number of edges of G crossing pi minus the number of edges of F crossing pi by this quantity, the number of edges of F that stay in the partition minus the deficit. And what we do have is a lower bound on the left-hand side in terms of the matching number. And here's the plan. We're given an F and its optimal partition pi, and Koldon and Gowers guarantee that the number of edges that do not cross the partition is much smaller than n squared p. However, we know that it's non-zero because otherwise the graph will be R-partite. Now, we would like to find some Q, a subgraph of F, and some number dq that depends only on Q but not on F, but every time for an F we pick a Q, we want this dq to be at least as large as the number of edges of F that do not cross the partition. And would like to union bound now over all Q, meaning to show that the probability that we have some Q and some pi for which the inequality that we seek does not hold is small. Now, in order not to deal with kind of this deficit here in the upper bound, note that this will follow if we show that the probability that we have some Q and some pi with deficit at most dq that the matching number will be most dq will be small. Because if the deficit is larger than dq, then this is already negative. So the matching number cannot be smaller than a negative number. And therefore, this is what we need to prove. We need to show that for all graphs Q in our family, if they're contained in G, then regardless what partition we take, if it's a partition which is close to an optimal partition of G, then there needs to be many pairwise edge disjoint copies of our graph H, which are supported on Q. Now, here I repeated the plan again. How do we do it? And the answer is, we do it using Janssen's inequality. So Janssen's inequality is a probabilistic inequality which says that give me a family of copies of some subgraph in Kn, and I can tell you, bound the probability that none of them appears in G and P. And this will be equivalent to bounding the matching number less or equal to 0 if we have no copies. However, one can modify this inequality in a fairly straightforward way to have an inequality which will also be able to bound this lower tail event and get a similar upper bound. So I won't get much into technical details, but if you're familiar with the book of Allen and Spencer, there's a chapter there in the chapter of Janssen's inequality, which deals with max disjoint families, and this is where this idea is developed, and this was our inspiration. Now, the kind of the take-home message is that if you're willing to work a bit, this is maybe about 10 pages of calculations and kind of several weeks of suffering for us, then you will be able to prove that if I allow you to fix the partition, then you get a bound which is strong enough even to allow a union bound over all Q. So if in this problem you only had to consider a fixed partition, then you would be able to get away with Janssen's inequality. And why is this true? Note that if we sum over Q which contain precisely one edge, then what allows this calculation to succeed is precisely our assumption that when we add one edge to a fixed partition and we calculate the probability that we have no crossing copies of H, then this will be 1 over n squared of P, and we have n squared edges here, each of them appears with probability P, so the size of the union bound is roughly n squared P. And it turns out that when Q gets larger, 2 edges, 3 edges, and so on, then this bound on the probability decays faster than the number of graphs that you have to consider. So really one edge is the bottleneck here. Another take-home message from here is that when we consider Q which are somewhat large, such that this probability bound is better than exponential in n, then the fact that we're dealing with a fixed partition is no longer a problem because they're at most constant to the n partitions. And if the probability bound here is better than exponential in n, then we can just absorb the union bound. And the challenge is really the one edge case. Suppose that our graph Q has exactly one edge, and we want to bound the probability that there are few copies of H that are supported on this particular edge, but this has to be true for all partitions which are close to the optimal partition, meaning that the number of edges crossing is not smaller than a constant additive factor. So this is the real challenge in this question. And how to deal with this enormous union bound. And here we got inspiration from really wonderful ideas from the paper of DeMarco and Kahn. So what DeMarco and Kahn realized that even though there are possibly tons of optimal partitions for a random graph, then these partitions tend to cluster together in the following precise sense. So suppose we have a graph G and 2 of its vertices. We'll say that these vertices are equivalent if they will lie in the same part of every largest R cut of this graph. And we will call G rigid if the number of equivalent pairs is roughly 1 over R proportion of the edges of Kn. So note that this is an equivalence relation. So the equivalence classes will be just complete subgraphs of Kn. And the definition of rigidity basically says that a graph is rigid if we have R equivalence classes and each of them of size roughly n over R. And indeed, this is what the claim says. If G is rigid, then there are equivalence classes of this relation, S1 up to SR of size n over R plus minus little of n each. And this set is called the core of G. So what does it mean? If the graph is rigid, it means we have R set of size n over R. And we know that every largest R cut puts all of these sets in different classes, meaning that all the edges crossing between the different SIs will definitely belong to the largest cut. Now, here's the key probabilistic lemma. Suppose that for every tuple of disjoint sets, we have some event which is decreasing and determined by the edges crossing this partition S1 SR. So our decreasing event will be there are few copies, say, of H, say, of the triangle, which cross between the sets S1 up to SR. Now, the probability that G and P is rigid with this core, and the core satisfies this decreasing event, is at most an R factorial, so a small constant factor, times the largest this probability can be over all ordered tuples. And this is the lemma which essentially reduces a union bound over all max cuts to just the worst case. So if we can show that for every fixed partition, we have a good probabilistic estimate, then this allows us to lift this probabilistic estimate to all the largest cuts. At the slight cost of saying, instead of looking at copies of H crossing the entire cut, we'll only look at the ones which cross the core. But core is most of our cut, because the cut, so the sum of sizes of the cores is roughly n minus little of n. So most of the edges will actually be crossing all the largest partitions, and we'll only look for our pairwise edge disjoint copies of H in this core of the graph, which will appear in every largest partition. Now, how does one use the lemma? So this potentially would allow one to deal with largest cuts, but our plan asks us to deal with also cuts which are only approximately larger. So they have the deficit, which can be as large as n squared p. And here I will say just kind of very, very few words. This is the bad event whose probability we have to bound. We have some partition with small deficit, so close to maximal, where the maximum number of pairwise edge disjoint copies of H supported on a graph Q is small. Now, we pair it with the event that G is rigid, and the number of these copies which cross not pi, but the core of G is not much larger. So the difference here is instead of pi, I will write a core. Instead of a dq, I'll have some large constant times dq. Now, the key idea, which I won't have time to elaborate on, is that we will construct using a sequence of edge additions and removals, a many-to-many relation. We'll take a graph which satisfies this bad event, and we'll transform it into a graph which satisfies this bad event. In the sense that there will be many ways, relatively many ways to transform a graph from this event to a graph in this event, but relatively few ways to arrive at a given graph here from a graph on the left. So we constructed this auxiliary bipartite graph. We want to bound the probability of that by the probability of that. And we can do it by taking the ratio of the small divided by the large. So it's kind of another installation of the very powerful method of switchings in probabilistic combinatorics. And the corollary would be that now, instead of bounding the probability of a graph belonging to this bad event, which we're interested in, is we bound the probability of GNP falling into this bad event, which this correlation lemma of DeMarco and Kahn reduces to bounding the probability of something happening in a fixed partition. But we already know how to deal with a fixed partition because we have Janssen's inequality and some patience to perform a 10-page calculation. And this is how the argument can be finished. So this is really, in a nutshell, kind of defining this sequence of edge additions and removals. So defining this relation takes work, and even I didn't tell you the entire truth. So there's a lie which hides in here, but at least globally, this is this is the high-level idea of how the analysis is performed. And let me finish, or maybe close, with just one summary slide. So we took an edge critical graph H, which is moreover strictly two balanced, and what we can prove is that when we're above this critical probability, then GNP is asymptotically almost surely H Simonovits. Now, what is this critical probability? For a fixed balanced cut, partitioned into R parts, balanced means the sizes of the parts are the same or nearly the same. The expected number of edges that do not cross the partition that we can add without creating a copy of H is approximately 1. So this is the point where we take a largest cut and we can add an edge if this cut was fixed. Now, a corollary of the theorem is that for every largest R cut, we cannot find such an edge. Because if we did find an edge that we can add without creating a copy of H, then you would have an H-free graph, which is by 1 larger than the largest R-partite graph. And what is open is that if we're slightly below this critical probability, then it's enough to find 1 largest cut for which we can find an edge, so that if we add it, it will not close a copy of H. Even the case of a triangle. So you can easily calculate this constant, and then suppose you're below this threshold, can you prove that there is some largest bipartition of GNP so that if you add 1 edge, you will not close a copy of the triangle? And the definition of the threshold says that if this cut was not the largest cut, but the fixed cut, then this you could show easily. And I think I will stop here. So thank you.
Thank you, Wojciech, for a nice talk. Questions? So maybe I have a question. So Wojciech, so this lemma of Kahn and DeMarco mentioned, it's a very interesting phenomenon. So do you know, like, since you work a lot on various questions in random graph, do you know a similar kind of statement in other situation where, right, this union bound over so many events can be reduced to the maximum times some small constant, right? You really kind of, right, by...
Yes, I actually, this is the only place where I've seen it. To be fair, I haven't read the Brightwell, Panagiotou, and Steger paper. This lemma is not very difficult to prove.
No, right, but just the phenomena is very interesting.
Yeah, it's a very clever application of Harris's inequality.
Of which inequality, sorry?
Of Harris's, FKG.
FKG.
Because, I mean, the idea is that if you add edges crossing a core, then it's still a core. So this event is increasing, but we assume that this event is decreasing, which means that the probability of the intersection is the product of the probabilities. But since core is unique, then these probabilities will sum to at most R factorial.
I see.
So it's really easy to prove.
I see.
But kind of the magic in it is, I think, the notion of a core
So somehow the core makes this probably kind of events disjoint, and then you sum up and not take union.
Yes. The fact that you have a unique core, instead of many possible cuts, you have a unique core, which means that this sum will be constant. So it's kind of essentially as good as saying that there's a unique largest cut.
I see. Interesting. But you only saw it basically.
We only saw it in the paper of DeMarco and Kahn. Actually, only in the clique paper. The triangle paper doesn't need it. There's kind of a cheaper way that you can get away with. And that's why also, but kind of using this lemma is already more difficult. The paper of DeMarco and Kahn is 69 pages. So ours will be round about 40.
I see. Look, it's a
major
20% improvement. I see. More question, please.
Hi, Wojciech.
Hi, Raiko.
Thank you for a nice talk. Maybe can you tell us a bit at which point does your proof depart from the DeMarco Kahn proof for the KR+1 case?
Yes, it departs here.
Okay.
So kind of, I think the reason why our proof is significantly shorter is that they only studied the lower tail of the number of such copies, and they had to kind of deal a lot with double counting. So they need to remove an edge from each, but no edge is removed too many times. And kind of what we realized is that if you just look for pairwise edge disjoint copies, then you can get similar estimates with just a little more work using Janssen's inequality. But you don't have to deal with the overcount. I mean, there's lots of other differences, but this is the main one.
Yeah, thanks. That answers.
Hello. My question is, your conclusion is a critical value of probability, right? You have
yes.
shown it is threshold, or you haven't shown it.
So we only showed one part. So we only showed that if you're above this conjecture threshold, then your statement is true. But our lower bound, which is a slightly different argument, using the fact that if you look at the edges in GNP which are not contained in any copy of H, then they induce a graph with large chromatic number. It gives you a constant which is different than this constant theta that they define. So there's a constant gap in the threshold. And we believe that kind of our condition is optimal, but unfortunately we cannot prove it. And the reason we cannot prove it is that in this lemma, we cannot invert the inequality because we use Harris's inequality. We cannot invert it. This is increasing, this is decreasing. And to prove the complementary, to prove the zero state, we need to invert this inequality, and we don't know how to do it.
Okay, you means that you give the magnitude is correct, but the constant maybe you haven't shown it, right? You give the
yes.
Okay.
We believe this is the constant, but so DeMarco and Kahn conjectured a different constant. Unfortunately, their constant was lower than ours, so we cannot even disprove their conjecture, because if they conjecture the threshold which is above ours, they would disprove it. So kind of morally, their guess, I guess, was wrong, but we cannot prove it.
The log factors to the 1/2 is interesting, because I noticed the other phenomenon, the threshold is the log n, but here is log n to the 1 over.
It's just so the power of the log. A log appears often in such problems if you have some coupon collector kind of behavior, that you have some local events that have to appear everywhere, and here essentially every edge needs to be in a copy of a triangle, and you have polynomially many edges, and the probability is to get that this happens with probability that beats this polynomial factor. You need to add the log, which will then square in the exponent, because a triangle has 1 + 2 edges. this is how the log appears. And maybe let me add that there's kind of a different version of this problem where instead of looking at the largest, say, triangle-free subgraph of GNP, you look at the structure of a typical triangle-free subgraph with a given density, and there such threshold phenomena were established. This is work of Osthus, Prubel, and Taras, and also a paper of Jozsef Balogh, Rob Morris, Lutz Warnke, and myself. So we're able to prove that also the corresponding zero statement, but there you don't need to, so you can essentially fix a partition. So that problem is easier in this sense.
Thank you for your answer. Thank you.
Actually, Wojciech, so this both gave me kind of another question, this discussion. So you said that indeed, right, you cannot reverse this Harris inequality. Actually, do we have some good understanding, you know, when, like, what are the extremal cases when the Harris inequality close to equality, right? Because that's what, I mean, maybe in such a generality, it's a hard question, but that's roughly what you would need.
Yes, yes, you're absolutely right, but yeah, I'm not an expert here, so but I'm not aware of anything like that.
Yeah, I also never heard, but it seems like a natural question to try to understand, right?
I agree. Yeah, it's just like, unfortunately, it's a complicated distribution. You know, the distribution of edges crossing a max cut in GNP because you have so many potential max cuts.
Mm-hmm. I see. Okay. More questions? So if not, let's thank Wojciech again. So great, thank you, Wojciech. And yeah, and next week it would be Tibor Sabo. So the title and abstract are online, and I hope to see all of you again. Thanks, Wojciech, again.
Thank you for the invitation. Thanks for coming.
Bye-bye.
Happy Pi Day, everyone.
Happy Pi Day, exactly. Yeah.